Okay. So, let us remind ourselves again that what we have learnt about the Fourier transform. So, the Fourier transform was defined as f tilde of k is equal to 1 over root 2 pi integral minus infinity to plus infinity f of x e to the minus I k x dx. Okay. If you had this sort of expression, you could also write f of x is equal to 1 over root 2 pi integral minus infinity to plus infinity f tilde of k e to the plus I k x dx. Okay. So, we naturally like to think of this as an expansion. So, you are expanding the function in terms of e to the I k x, where sorry, this should be d k, where k is a continuous variable. Okay, k is a continuous variable, okay, that goes from minus infinity to plus infinity. Okay. Now, this sort of expansion right now it just looks like a mathematical trick, but we will see a real application of this shortly. Before that, I want to mention a couple of things. One is that if you look at different books, they might use different definitions of Fourier transforms. So, some books might use a plus sign here, might use a minus sign here instead of a plus. Some books will not have the factor of 1 over root 2 pi. So, they will have just this term, and then they will take the 1 over 2 pi here. Okay. But these will just cause small changes in the numerical factors, but the method is fairly general and you can still apply it. So, so the lesson I want to mention is that there is no unique definition of Fourier transform. Each book or each author chooses to define it in a way convenient for them. Okay. The other thing we should mention is that in order for this to be well defined, especially when k equal to 0, you can see that integral f of x dx should be well defined. Okay. So, f should be piecewise continuous in order for this to be defined. Okay. So, this is like a transformation of variables. You go from a function of x to a function of k. Okay. So, you are changing from x to k. Okay. So, you are transforming your variables of your problem from x to k. Okay. So, it is similar to that, and this is what we will use in order to solve differential equations. Okay. The other thing which I mentioned was that suppose h of x equal to, if h of x is df by dx of x, then h tilde of k is equal to I k f tilde of k. Okay. This is a property that if the Fourier transform of a derivative is nothing but I k times Fourier transform of the function. The other important property that we saw is that if g of x is equal to the convolution of f and g. Okay, f star g is a function of x, okay, and this function we wrote as integral f of x minus x prime g of x prime. Let me call this h of x. Okay, so I will call this h of x. Then h tilde of k is equal to square root of 2 pi times f tilde of k g tilde of k. Okay. And this is the convolution theorem. This is called the convolution theorem. Okay. Okay. So, this is called the convolution theorem. Okay. So, now let us look at an example of how we use Fourier transforms to solve various problems. Okay. The problem that I will take is a problem in conduction of heat. Okay. So, so in this problem you consider, let this be the x direction, and you imagine that you have a very long bar, a bar of some material that is very long. Okay. And this bar extends infinitely long in this direction. Okay. So, it is a one dimensional bar. Okay. And this bar the temperature of this bar is not the same everywhere. Okay. So, the temperature the same everywhere. So, the temperature is different here, it is different here, it is different here. Okay. So, u is a function of x. Okay. And then the other thing that happens is that suppose you program the bar with a certain temperature. Let us say initially you keep the bar at constant temperature, but you make it very hot in one side, then over time the temperature will change. So, the temperature is not only a function of x, but it is also a function of time. Okay. So, the temperature is both a function of x and time. So, that means at any point the temperature of the bar keeps changing with time. So, suppose you go to a point x and you look at a time t, the temperature of the bar is a function of both x and t. Okay. So, now let us consider the problem. Okay. The problem is we want to start with some condition. So, at t equal to 0, u of x 0 is equal to f of x. That means it is some function of x. That means you could choose f of x to be any form, that it's 0, it is you could choose f of x to be a constant, for example, or you could choose f of x to be oscillating function. Okay. So, it is some function which describes what the initial temperature of this bar is. Okay. So, this is at t equal to 0, and now you want to find u of x t. Okay. So, in order to do this you should know how u of x t varies, and you are told that the equation of motion says that the rate at which heat flows out, okay, at any point, this is given by c square dou square u by dou x square. So, this is the Fourier's law of heat conduction, which says that the rate of flow of heat is related to the gradient of temperature, or the second derivative of temperature. So, what you have to do is to solve this differential equation. So, you need to find a u that satisfies this differential equation and this boundary conditions. So, mathematically what you need to do is to solve this differential equation with these boundary conditions. Okay. Now, if you want to solve it, if you try to solve it, you have a partial differential equation in both x and t. Okay. If there is not much you can do. If you try to separate variables, then you will get that both of them have to be 0, both of them have to be constant. So, you will just get a trivial solution when u is constant everywhere. Okay. But you want a solution where so that can never satisfy these boundary conditions unless f itself is a constant, but if you have an arbitrary function f, then you cannot solve this equation by simple separation of variables. Okay. So, what we do is you transform x to k. Okay. So, when you transform x to k, u of x t goes to u tilde of k t. Okay. So, x to t, and when you do this you keep t the same, okay, you do not do anything to t. Okay. So, what we shall do is take the Fourier transforms on both sides, and what do we get? Let us see what we get. So, you have d by dt of u of x t. When you take the Fourier transform of that, the transformation only acts on x. So, it goes within this t. So, what you get on the left hand side is d by dt of u tilde of k t. Okay. So, that is the left hand side. The right hand side you get c square times Fourier transform of this derivative. Okay. And this is where you use this theorem, that Fourier transform of the first derivative of function is I k times f of k. So, Fourier transform of the second derivative will be nothing but I k square u tilde of k t. Okay. So, you can show this. Okay. So, now your equation becomes is equal to minus k square c square u tilde of k t. Okay. So, that is what happens to your Fourier. So, your partial differential equation now became a much simpler looking equation. Now, you can solve this for u of k t, okay. Since this is a just first order differential equation in time, this is a first order differential equation in time. Okay. So, I can just integrate it out, and I can so if I integrate it out, I will get u. So, let us do it explicitly, du tilde of k t by u tilde of k t is equal to minus k square c square t dt dt. Okay. And this simply implies u tilde of k t equal to u tilde of k 0 e to the minus k square c square t. Okay. So, u tilde at k of k at time t at time 0 times e to the minus k square c square t. So, and that is what you get when you integrate this. Okay. So, this is good, you got u tilde of k t in terms of u tilde of k 0. Now, what is u tilde of k 0? U tilde of k 0 is nothing but the Fourier transform. This is nothing but the Fourier transform of u of k 0 of u of x 0. So, the Fourier transform of this is equal to this. Okay. So, what we have is that u tilde of k 0 equal to Fourier transform of u of x 0 is equal to f tilde of k. Okay. So, it is a Fourier transform of this, Fourier transform of f of x. So, whatever f of x I am given, okay, whatever your problem specifies the f of x, you take the Fourier transform of that. So, then you get the equation u tilde of k t is equal to f tilde of k e to the minus k square c square t. Okay. So, this is the expression. Okay. Now, what you wanted was u of x t, okay, but what you got is u tilde of k t, and then to go from u tilde of k t you just take an inverse Fourier transform to get u of x t. So, this procedure is an inverse Fourier transform. So, what you have to do is to take the inverse Fourier transform of this. So, what you will say is that u of x t is equal to just the inverse Fourier transform of this quantity. Okay. Now, you have to take the inverse Fourier transform of a product of two functions. Okay. So, now you use your convolution theorem. Okay. So, let square root of 2 pi times g tilde of k is equal to e to the minus k square c square t. Okay. So, then the inverse Fourier transform of this is g of x. Okay. So, if the inverse Fourier transform of this is g of x, then this is just then u of x t is equal to inverse Fourier transform of f tilde of k square root of 2 pi f tilde of k g tilde of k is equal, and the inverse Fourier transform of this from convolution theorem is just f star g of x. Okay. So, from the convolution theorem this is just this. Okay. So, what you have to do is you need to know. So, f star g of x is integral f of x minus x prime g of x prime d x prime from minus infinity to plus infinity. Okay. Now, f is known. Okay. So, what you have to do is to determine g. If you know g, then you have the solution. So, u of x t is equal to this. Okay. So, the last step is to determine g of x. So, g of x is the inverse Fourier transform of this function divided by square root of 2 pi. So, what you have is that g of x is equal to inverse Fourier transform of e to minus k square c square t divided by square root of 2 pi. And what is the inverse Fourier transform of this? You can show this. So, this is equal to integral e to the minus k square c square t 1 by root 2 pi, okay, and then you have another 1 by root 2 pi. Okay, so, this is this function times e to the I k x d k. Okay, so, this is the g of x. Okay. Now, you can actually calculate this. It's not hard to calculate this, and your answer will come out to the following. Okay, before I calculate that, I'll just mention how you do it. So, you have 1 over 2 pi integral e to the, I'll write this in the following form, minus c square t k square and then I had what I'll have here is minus I x by I x by c square t into k. Okay. So, when I multiply these two, I will get plus I k x. Okay. And so, I have this, and just to carry out this Fourier transform, I will complete the square. So, if I complete the square, then the remaining term will be minus x square by 4 c 4 t square. So, this okay. So, and then what I have to do is so this times d k, and then since I multiplied by e to the minus e since I added this extra term, I have to do e to the I have to put the opposite of that. So, that will be c square t minus c square t x square divided by 4 c 4 t square. Okay. So, what you can see is that I multiplied this term and then I multiplied by the inverse of that. Okay. So, this is a simple trick to evaluate the Fourier transforms. Okay. So, then this just becomes 1 over 2 pi integral e to the minus c square t times k minus I by 2 c square t I x by 2 square t 2 c square t whole square, okay, d k into e to the, now I will just simplify this. So, minus x square by 4 c square t. Okay. And now, this integral can be done fairly easily. This is just a simple Gaussian integral. Okay. Instead of having e to the minus a x square, this is just c square is the c square t is the constant. So, I can just write this integral 1 over 2 pi root pi divided by c square t. Okay. So, this whole integral from minus infinity to infinity is just root pi by the coefficient of the Gaussian term, and that is just root pi by c square t. Okay. And this thing multiplies e to the minus x square by 4 c square t. Okay. So, this is the answer that we were looking for. Okay. And this is the final answer that you will get using this calculation. So g of x has this form. Now you can take this and you can substitute here, okay, and you will get the form of u of x. Okay. So what we saw was that starting from a very complicated looking partial differential equation, we could use the Fourier transform method, and we could very quickly arrive at the solution. Okay. So when you put all of it together, what you will say is that you will put this g of x here, you know the form of, we are given the form of f of x, whatever form of f of x you are given, you can do this integral. Okay. So the final solution u of x t integral f of x minus x prime into I had a 1 over root 2 pi here. Yeah. So I had a 1 over root 2 pi. So if I take that with that root 2 pi, so I'll get 1 over 2 c root pi t. Okay. So this is I'll take the c outside, and then I have a 1 root 2 pi will cancel. So I'll be left with a root pi t. Okay. F of x minus x prime e to the minus x square by 4 c square t d x prime square. Okay. So this is my final answer. Okay. Okay. So this is a very powerful result that we got, because I don't need to specify what my function is. Okay. And still I can solve the differential equation. Okay. So I solved the differential equation even though I didn't tell you what f of x was. So if you remember, the differential equation was dou u by dou t of u of x t is equal to c square dou square u by dou x square. Okay. With the condition that u of x 0 is equal to f of x. Okay. So given any form of f of x, you can go ahead and you can say that this is the form of the solution. Okay. So we solve this differential equation using this method of Fourier transforms, and in fact Fourier transforms is one of the most commonly used methods to solve differential equations. Okay. The other thing I want you to notice was that g of x was this, where g tilde of k, if you remember. Okay. So g tilde of k was e to the minus k square c square t divided by root 2 pi. Okay. So g tilde of k is nothing but this quantity. Okay. Now this is another interesting feature. You notice that g of x is a Gaussian function. So it is some constant multiplied by it is e to the minus x square into some constant, and the Fourier transform is also a Gaussian function, e to the minus k square into some constant. Okay. So this, what we see is that Fourier transform of a Gaussian is also a Gaussian. Okay. So this is a, we also noticed, I will just write it down again. So if g of x is equal to 1 over 2 pi, I can take this pi inside, 1 over 2 root pi c t e to the minus x square by 4 c square t, then this gives you g tilde of k is equal to 1 over root 2 pi e to the minus k square c square t. Okay. So g tilde as a function of k is also this. So suppose g of x is equal to e to the minus a x square. Okay. Then you can immediately see, you can just compare the terms, and you can say that g tilde of k. Okay. So instead of 1 over 4 c square t, I had a. Okay. So wherever I have c square t, I replace it by 4 over a. Okay. So you can just go ahead and do this, and and what I will get is the following. Let us see, and then we have to put the constants properly, 2 pi c square t. Okay. So, let us 2 root pi. So, with some constant of proportionality, this will just be e to the minus k square by a square, 4 a square. Okay. So, let us check if that is correct. So, a can be compared with c square t. So, therefore, c square t is equal to 1 over 4 a square. Okay. So, c square t is 1 over 4 a square. So, you get this, okay. And then c square t is 1 over 4 a square. So, what I have to do is to multiply this out. So, it is let us see 2 root pi c square t divided by root 2 pi. Okay. So, that is what I will get. Okay. So, so I can cancel this, I get root 2 c square t, and this is c square t is just a is 1 over 4 c square t. So, this is c square t is 1 over 4 a square. So, square root of that is 1 over 2 a. So, you just get 1 over a e to the minus k square by 4 a square. 1 over c square t is 4 a square. Okay. 4 a, sorry, a. So, 1 over a. Okay, let me make sure I got that right. So, so what you got is the following. The final result you got is that if g of x is e to the minus a x square, then g tilde of k is 1 over root a e to the minus k square by 4 a square. Okay. So, that is the result that we have shown. Okay. So, so let us look at this a little more. So, I will just write it again here. G of x is equal to e to the minus a x square, g tilde of k is equal to e to the minus k square by 4 a square, okay, multiplied by this constant 1 over root a. Okay. Okay. So, let us, this function is called a Gaussian function. So, this is a Gaussian function. So, it looks like this. So, its maximum is at x equal to 0. So, as a function of x, g of x looks like this. Okay. Now, the width at half maximum. Okay. So, this is, if you can calculate this. So, when this width is nothing but 1 by 2 root a. Okay. Now, so the width is inversely proportional to square root of a. And in this case, what you have is the following. K. Okay. And let us not bother about the constant, but if we ignore the constant, what we will see is that this is also a Gaussian. Okay. And now, the width is 2a, or sorry, width is just a. Okay. Width is just a, no, sorry, root 2a. Okay. Okay. So, the way to find the width of a Gaussian is basically Gaussian function is represented by e to the minus x square by 2 sigma square, where sigma is the standard deviation or the width at half maximum. Okay. So, in this case, this width is 1 over 2 root a. In this case, the width is root 2a. Okay. So, what we have shown is the following, that if A is very large, okay, then that means you have a very narrow Gaussian. In X space it is very narrow, this width is very small. If this width is very small in X space, then this width becomes very large in K space. Okay, so that means width in K space is inversely proportional to width in X space. Okay, so if you have a very narrow function in X space, it becomes a very wide function in K space, and vice versa. Okay, so if you have a very wide function in X space, it becomes a very narrow function in K space. Okay, an extreme example of this is suppose you have a constant function. If f of x is constant, okay, so f of x is constant. Constant can be thought of as a Gaussian of infinite width. You can think of it as a Gaussian function where the width of the function is infinite. Okay, so as you make this wider and wider, okay, you will go finally to something that is almost a constant. Okay, the f tilde of k equal to delta of k. Okay, it is proportional to delta of k. So if you have a very wide function in X space, then you get a delta function. So in this case you have f of x as some constant, then f tilde of k becomes a delta function. Okay, so it becomes a delta function. So a very wide function becomes a very narrow function, and this is a usual property of this Fourier transforms. Okay, now how do you show that f tilde of k is a constant? How do you show that f tilde of k is this delta of k? To do this, you just use the definition of f tilde of k. So what you say is that f of x equal to constant equal to a, say it is a, then f tilde of k is equal to integral f of x e to the minus I k x dx 1 over root 2 pi. Okay, so that is just now this is a constant a that I take it outside. So a times a by root 2 pi integral e to the minus I k x dx. Okay, then this we already said this is nothing but a delta function in k. So this is equal to with some constants, let me get the constants right. So this quantity with the 1 over root pi, so this is just a times delta of k. Okay, so therefore if you have a constant function, then its Fourier transform is a delta function. Okay, so this is a property of Fourier transforms, that if you have a function that is very narrow in one, similarly the Fourier transform of a delta function, if you had a delta function, its Fourier transform would be a constant. Okay, so f of x equal to delta of x. Okay, then f tilde of k is equal to 1 over root 2 pi integral delta of x e to the I k x dx e to the minus I k x dx. Okay, so and you can immediately see that this is equal to, so that means if I want to do this integral, then I can do this integral by just writing this as 1 over root 2 pi, then e to the I k, and instead of x I put 0 because I have delta x minus 0. So I k is 0. Okay, so I just put the value of the function at x equal to 0, and this is just 1 over root 2 pi. Okay, so f tilde of k is just a constant. Okay, so this is the property of this Fourier transforms. Okay, so next we will look at some pairs of Fourier transforms. Okay, so now we list some Fourier transform pairs. So these are all what are called as Fourier transform pairs. Delta of k. So, but on the other hand, if I had taken f of x as square root of 2 pi times delta of x, f tilde of k would have just been 1. Okay, so they always have this inversion relation. Okay, then if f of x was e to the I times a constant times x, okay, then the Fourier transform of that you can easily show this is square root of 2 pi times delta, instead of k you have k minus k 0. Okay, this is fairly easy to show. Then we will show this in a minute. If you had f of x is e to the minus a absolute value of x, then the Fourier transform is root 2 by pi a over k square plus a square. Just to show this, I will show it to you really quickly. So, f of x is, so the Fourier transform is e to the minus a times absolute value of x dx from minus infinity to infinity into e to the minus I k x dx. So, the Fourier transform is this, and this is equal to with a 1 over root 2 pi. Okay, so this is equal to now we can write this as integral minus infinity to 0 e to the minus a times. Now, absolute value of x, when x goes from minus infinity to 0, x is negative. So, absolute value of x is minus of x. So, you have plus a x e to the I k x dx, then plus integral from 0 to infinity e to the minus a x. So, when x goes from 0 to infinity, then absolute value of x is just x. So, you get this e to the minus I k x dx. Okay, and each of these can be evaluated. So, this is integral minus infinity to 0 e to the x a minus I k dx plus integral 0 to infinity e to the x minus a minus I k dx. Okay. And each of these is an exponential function. So, so you can just integrate this out. So, this will be e to the x a minus I k divided by a minus I k from minus infinity to 0 plus e to the x minus a minus I k divided by minus a minus I k from 0 to infinity. Okay. So, now the upper limit corresponding to x equal to 0 will give me 1 over a minus I k. The lower limit corresponding to x equal to minus infinity. So, when x becomes minus infinity, you get e to the minus infinity into a. Okay, a is I should mention. So, a is greater than 0. Okay, so in this case, a is assumed to be greater than 0. Okay, so since a is greater than 0, then e to the minus infinity into some positive number, that gives me e to the minus infinity. Okay, and we don't even need to worry about the e to the I k x. At the lower limit, I will just get 0. Similarly, in this case, at the upper limit I will get 0, because e to the infinity into minus a. So, that is e to the minus infinity. At the lower limit, I will get 1 over minus a minus I k. Okay. So, so what I will get is 1 over a minus I k plus 1 over a plus I k. So, I can take all these minus signs together. So, I have 1 over a minus I k plus 1 over a plus I k, okay, and this is just you can multiply it out. So, I k plus a minus I k. So, that is 2 a divided by a square minus k square, a square plus k square, sorry, a square plus k square. Okay. So, that is what you will get with this. So, should have had a 1 over root 2 pi, have a 1 over root 2 pi hanging around everywhere. Okay, so this whole thing should divide by root 2 pi. Over root 2 pi. Okay, and this whole thing is 2 pi. Here also you have 1 over root 2 pi, and you have root 2 pi, and that is just this answer. Okay, so when you take 1 over root 2 pi into a divided by a square plus k square, so you will get exactly this answer. Okay, so we have shown this relation. There are few more Fourier transform pairs which you can also find out. I will just write a general shifting property, a very interesting property called a shifting property. So, f of x minus a. Okay, so the Fourier transform of f of x minus a is related to Fourier transform of f tilde of k. Okay, but this relation is the following. So, it is f tilde of k into e to the minus I k a. Okay. So, if you shift your so this is just f of x, instead of x my argument is x minus a. Okay. Then my Fourier transform will just be f tilde of k multiplied by e to the minus I k a. So, this is called the shifting property. And it works the other way also. So, if I had f of x into e to the I a x, or sorry, e to the I a x, yes. Okay. Then I would just get f tilde of k plus a, or k minus a, sorry, minus a. Okay. So, it works both ways. Okay. So, this is a property of this Fourier transform. Okay. And that is what we used right here. Okay. So, this is 1 into e to the I k 0 x. Okay. So, the Fourier transform of this is the same as the Fourier transform, but not at k, but at k minus k 0. Okay. So, that is this shifting property of Fourier transforms. So, the Fourier transforms, the way we define them, there is a nice symmetry to the relations, and you can do many more such Fourier transform pairs. The last thing I will mention is the following. We'll look at some applications of Fourier transform in real chemistry problems. Okay. I'll just mention another interesting property of Fourier transform, which is called the Parseval's theorem. Okay. This is a theorem that makes Fourier transform very useful for in spectroscopy. So, many of you might have heard of things like FTIR or FTNMR. So, Fourier transform IR or Fourier transform NMR. Okay. So, this makes use of a very powerful theorem of Fourier transforms, that is called Parseval's theorems. So, I will just state it for now, and then we will close this discussion on Fourier transforms. We will look at some specific examples in the next class. So, so this is called Parseval's theorem. And this basically states that integral f of x square dx is equal to integral f tilde of k square dk. Okay. So, this theorem states that the area under square of Fourier transform is square of f of x is same under the area of the square of f tilde of k under k. Okay. And this means that if f of x is, let us say, some electric field, okay, that is being applied. So, when you are doing spectroscopy, you are shining light. So, light has some electric field component. Okay. Then the square of the amplitude of the electric field is related to the intensity. Okay. So, what you are saying is that the total intensity is and the Fourier transform of the intensity is what is called the power spectrum. So, this connection between power spectrum and intensity is what allows you to use Fourier transforms to do spectroscopy. So, this is something that is very useful in in spectroscopy. Okay. And so this is something that's used a lot. In fact in spectroscopy you do your variable x instead of your variable x is your time. So in spectroscopy typically you have time t and you transform to frequency omega. So the angular frequency omega. Okay. So this is what is typically done, and in some cases in some so this is done in spectroscopy. Okay. Now in X-ray diffraction, you use space r to Fourier space k. So wave vector k. Okay. So this is a 3-dimensional Fourier transform. So this is a 3-dimensional Fourier transform. Okay. Where instead of just having a 1-dimensional scalar variable x, you have a vector r with 3 components and you take its Fourier transform. So so in that case typically what you do is you have f of r to f tilde of k vector. Okay. So this is a 3D Fourier transform, and this is a very important component of X-ray diffraction. Okay. We won't be talking much about Fourier about 3-dimensional Fourier transforms, but in the next class I want to give an example of how we use of where this Fourier transforms appear very naturally.